Thank you very much, Dominique. Thank you for a nice introduction. Thank you also to the organizers for inviting me to this conference and inviting me to give a talk about hybridization of fuzzy sets and rough sets. Okay, so also a word of thanks, of tribute to our pioneers. Probably you know them, Lotfi Zadeh, scientist who in 1965 already proposed fuzzy sets as a way to model gradual information, and Professor Zdzisław Pawlak from Poland, who in 1982, like Dominic said, just 40 years ago, introduced the theory of rough sets. And as I understand, tomorrow there will be a presentation by Professor Skowron, also talking about the history of these 40 years of rough set theory. So as you can see in the slides, Professor Zadeh and Professor Pawlak were also good friends and met at quite a few conferences. And what I will try to show you in my presentation is that these theories that they presented, they are also like very good working together to produce some hybrid products. So I don't expect that you have previous experience with either fuzzy sets or rough sets. So it will be a kind of entry-level talk, at least in the beginning, for giving some background about what the rough set methodology precisely is. I will talk about the notion of inconsistency in data. Inconsistency occurs in a lot of different domains, but I will explain what it means specifically in rough set theory and in machine learning based on that. Then I will try to convince you that fuzzy sets can help to extend that theory, to make it more robust in the face of fuzzy information, graded inconsistencies. I will also outline a few opportunities for current and future research. So I will talk about the link with granular computing. So I will talk what we have achieved so far in our group was mostly lazy learning approaches, nearest neighbor-based approaches. We will show how, or I will talk about how that can be extended to also consider fuzzy rule induction. I will talk about the notion of robustness of fuzzy rough sets, specifically considering outliers which change the distribution of our information. And finally, also, since interpretable machine learning is a hot topic these days, I will say something about how fuzzy rough sets, how they can help us also in this aspect. So to start, a very simple machine learning problem. It's about getting a bank loan. So suppose we have a number of clients of a bank, and what we know about them, we know their debts, we know their salaries, and also we have like their portfolio, the amount of investments they have. And the decision in this case would be whether they got a bank loan, one, or they didn't get that bank loan. So a very simple problem of supervised learning, where we would try to find a good classification function that for future instances predicts whether the decision will be 1 or 0. Now, if we look at this data closer, we see that we have a problem, because we have two instances, number 3 and number 4, who are exactly the same for these parameters, for these first 3 attributes, but they have a different decision. Apparently, one of them got the loan, another one didn't get the loan. So if you think about learning classifiers, that's kind of a problem, because if even the teacher doesn't know what the right answer is for a case, how would the student supposed to be able to learn it? So that's quite an important problem for machine learning. So rough set theory will help us to model that kind of inconsistencies. Now, this is not, so this is kind of inconsistency occurs because two instances, 2 items are indiscernible. They are the same according to the data. Of course, this doesn't mean that they are the same clients. Maybe we missed some information which was crucial to determine the decision of the bank manager to give or not give a loan. So maybe we have insufficient information. It's also possible some mistake was made and apparently number 4 shouldn't have gotten the loan or number 3 should have gotten it. So the reasons for the inconsistency we don't know, but we do know that the inconsistency is there. Now, looking more closely again to the same data, we see that there are actually more inconsistencies, because if we look at number 2 and number 3, they are not the same. They don't have the same parameters, but we can see that number 2 has a higher debt, he has a lower salary and a lower portfolio. So in all aspects, he should be considered worse to get a bank loan. But apparently they did, number 2 did, but number 3, which dominates number 2, we call it dominating because it's better in all aspects, they didn't get the loan. So I think it's opposite, right? It's number 3 shouldn't get the loan, and number 3 should get the loan, but apparently did not get it. So in this case, we call it an inconsistency because of domination. So the first one was indiscernibility, now it's domination. And this kind of inconsistency would occur in monotone classification problems. So where we take into account the ordering of attributes. That is an attribute that we want to be as low as possible. The 2 other attributes, salary and portfolio, we would like to be as high as possible. And based on those, we would like to have consistent decisions. In general, by consistency, we mean, well, 2 instances would be considered consistent with respect to either indiscernibility or dominance if they exhibit a certain relation on the condition attribute. So one dominates the other or one is indiscernible from the other. Then we also want the same relation for the decision attributes. So the decision should either dominate or be equal to the decision of the other instance. Now, rough sets, as I told you, they would they will give us approximations of this data which are consistent. And here is the mathematical framework. It's actually quite simple. So the idea is we have a concept, like for instance, getting a bank loan. And we have a set of examples of that concept. So A, in this figure here, would be the sets of people who got the bank loan from our previous data sets. And apart from A, we also have an equivalence relation on the universe. So U, that represents all the objects, all the clients, and we divide them into little blocks. We have a partition, and each block contains clients, objects, which have the same values for the condition attributes. So number 3 and number 4 from our table, they would be in the same block here, right? So what we want to do now is approximate that set A using the equivalence relation E, using that partition. Yeah? And how can we do that? Well, we can do it in 2 ways, basically. We can look at objects certainly belonging to the concept. Those are called the lower approximation. So upper with a line below it, it's called the lower approximation. When does an object belong to it? Well, when its whole equivalence class, its whole block is fully included into the set A. It means that some objects from this class, from the lower approximation, for them it holds that all the objects that look like it also belong to the concept. On the other hand, so that was the red rectangle. For the green rectangle, that's called the upper approximation. There we only require that an object has a non-empty intersection with the concept. So it's good enough that at least one object from a block belongs to the set A for the whole block to be included in the upper approximation. So we can see the lower rectangle is inside of A, while the upper, the green rectangle is enclosing the set A. So we have a lower and an upper approximation. If we take our simple data sets, we can see that the lower approximation will include number 1 and number 2, but not number 4. Number 4 belongs to the concept, but there is some indiscernible object, number 3, which does not belong to it, so it's not included in the lower approximation. It is, however, added to the upper approximation, and moreover, number 3 is also there because of the same reason. 3 is indiscernible, is the same as 4 according to the data, and 4 is in the concept, so it will be inside of the upper approximation. That's what Pavlak introduced, had to do with equivalence relations. And equivalence relations would model indiscernibility, having the same values for the condition attributes. But I also talked at the beginning, remember, about dominating information, dominance information. So in order to also accommodate that, some researchers, Greco, Matarazzo, and Professor Slovinsky, also from Poland, introduced a generalization of the Pavlak framework. It's a generalization because an equivalence relation that is reflexive, symmetric, and transitive. In a dominance relation, we will give up the symmetry requirements. So we only have reflexive and symmetric. And in this case, instead of a partition, we would get a covering of the universe where the equivalence classes are replaced by two kinds of sets. Dominating sets, D plus of an object U, contains all those objects that dominate, that are at least as good as U, while the dominated set, D minus of U, would contain those objects dominated by the object U. So U itself and all the objects worse than U. And then in this framework, what we will approximate are called concepts of the kind at least or at most a given class. If we have binary classification, it's quite simple. At least class 1 means I can get the bank loan. At most class 0 means do not get the bank loan. So in the example I give, it will be quite simple like that. So an object would belong to that concept if all the objects dominating it belong to the concept, so it would belong to the lower approximation. And for the upper approximation, it means that there should be at least one object which our object dominates and which belongs to that concept. Again, an example. So in our case, only instance 1 would belong to the lower approximation. Instance 2 does not belong to it. Why? Well, because it is dominated by instance 3. Instance 3 is better according to the criteria, but it does not belong to the concept. So that's why we only have one object in the dominance-based lower approximation. In the upper approximation, we have the same 4 objects as before, for the same reasons explained. Now, there is also an important link with granular computing, which probably many of you also are familiar with, as a theory where we try to disentangle knowledge into small basic parts of knowledge called granules. And in the case of rough sets, of Pavlak rough sets, those granules would be the equivalent classes of the relation E, or in dominance-based, it's based on the covering of dominated and dominating sets. So basically in rough set theory, we call a subset of U granularly representable if it is equal to a union of those blocks in that diagram. So any union of blocks is called granularly representable. Now that's quite a mouthful, so we'll abbreviate that to simply consistent, with the understanding that if two objects are in the same granularly representable set, it means that they will either both belong to the concept or both not belong to the concept. Okay? So what's also important is that the lower approximation out of all those consistent sets, that's exactly the largest one, which is still included into our set A. And on the other hand, the upper approximation, that would be the smallest one, which encircles it, so which includes A inside of it. So that makes lower and upper approximation special from that point of view. As I said, in this figure, we are talking about an equivalence relation, but it can be generalized to a covering. like for instance, if we use the dominating sets or the dominated sets from dominance-based rough set theory. Also, maybe not so many people know that, apart from lower and upper approximations, other kinds of approximations also have been proposed. And one of them, which is interesting to mention, was due to Kotlovsky and Slovinsky, who in 2008 defined a so-called monotone approximation. So they did that in the scope of dominance-based rough sets, but since dominance-based rough sets generalize Pavlak rough sets, it also applies to the specific case of indiscernibility. And the idea of them was that instead of getting a lower or upper approximation, they just wanted to have a consistent set which is as close as possible to the original set. And as close as possible to measure that, they use some loss function, like mean absolute error, for example. So in this case, in the case of our bank loan, we could see, for example, that the gray figure here, not a rectangle anymore, that could be considered as most similar or closest to the original set A and still a consistent set. Yeah? So that kind of information is also or can also be used. Then, once we have these approximations, what to do with them? And actually, there's a wide array of applications of rough sets. I will be focusing mostly on those related to machine learning. Yeah? And the two core ones, let's say, are feature selection and rule induction. So by feature selection, what we mean, so given a data set with a number of conditional attributes or features, we want to select those features, that subset of features, which preserves the same consistency as the full set. So that kind of subset is called a reduct. So in general, data sets may contain some inconsistency. Of course, we cannot avoid that, but we can try to take away features without making the situation worse. Okay, so without adding additional conflicts between indiscernible objects belonging to different classes, for example. So that is one application. The other one, which I will talk more about, is rule induction. So for rule induction, we refer to the consistent sets from the previous slides. So we have the granules here, and we will use those to create rules. Okay? Various variety of rule induction algorithms was proposed, for example, the LEM2 algorithm, the ModLEM algorithm, and also for dominance-based rough sets, the DOMLEM algorithm. So those are rule-based algorithms that take the approximations as a start. Also, another different other kinds of supervised and unsupervised machine learning problems have been handled, like discretization, clustering, even neural networks have been made rough to some extent. Decision-making outside of that, and more theoretical topics are, for example, in modal logic. So the certainty and the possibility operator, they are linked to the lower and upper approximation, and also in domains like topology, we have links. But like the list is not exhaustive, there are a whole array of domains, and the rough set paradigm is actually something which is very is occurring very frequently in science. So far for rough sets. Now enter fuzzy sets. So I want to make a case why, in some cases, it's useful to consider gradual inconsistencies. In a sense that, for example, if we look at our data set again, number 1 and number 3, strictly speaking, they are not inconsistent, because 1, well, they got the loan, but they are different from 3 who didn't get the loan. But to some extent, they are similar. Their debt is not so high, and their salaries and portfolios are more or less the same. So we could speak, to some extent, of a conflict of an inconsistency. If we look at it from the dominance point of view, it's even stronger, because number 1 has a lower debt and a higher salary, but they do have a lower portfolio. So partly they are dominating number 3. So there is partly some inconsistency. Now, what we will do is we will introduce fuzzy relations to model that either dominance or indiscernibility. So to say that some objects are similar to some extent, or some object is dominating another one to some extent. Okay? And how to do that? Well, I'll give you a simple example, simple illustrative example of how we can do that. There is not one way to do it, but the idea is we will construct some relation which is actually a mapping which gives values between 0 and 1, expressing how similar the instances are. If the degree is 0, it means the instances are totally dissimilar. If they are 1, basically they cannot be discerned from each other. They are the same. We can do that on an attribute level. For example, looking at the attributes from the previous table. So we can take, for example, attribute number 1. We can normalize it. And we can check, or we can look at the absolute difference between values. Okay? We can take that difference divided by the range and maybe multiply it with some parameter. And then check, is this value between 0 and 1? So basically, we will be constructing a triangle which is centered around the value of one of the objects, for example, V. Sorry, how to get that okay. It's back, okay. So it will be centered around the value of a V, and like if we move away from that value, either to the left or to the right, the similarity degree becomes lower up to a certain point. In this case, I think 0.25 or 0.75, where the two instances would be considered not similar at all. So this is kind of a triangular way to evaluate to what extent two attribute values are similar. Of course, the shape is just chosen for simplicity. We can use a Gaussian curve here. We can use any other kind of function to model that, but the idea is we have values between 0 and 1. And we do that for every attribute. So for every A, we would have such a relation. And we can combine those relations, for example, taking the minimum. We could also take the average or the product or another aggregation operator, but in this case, we will simply take the minimum of them. Okay? And if we apply that to our data sets, we get kind of discernibility matrix like here to the right. Okay, so we can see that, of course, the diagonal is all ones, meaning every object, every instance is similar to itself to degree 1. It's also symmetric, because the similarity of U to V is the same as that of V to U. And what is also inside, but which is not so clear, is that there is some transitivity property, because an equivalence relation is supposed to be reflexive, symmetric, transitive. We will have a weakened transitivity property also applied to the fuzzy degrees. But that one maybe is not so obvious in the degrees, but we, by our choice of the indiscernibility relation, we can impose that. Okay, we can do something similar for dominance. And in dominance, so the idea is the same. We are looking for a fuzzy relation that will express for two instances to what extent the first will dominate the second. In this case, it's no longer symmetric, right? Because one is supposed to be at least as good as the other. So the kind of relation at attribute level will look a little bit more complicated. So we'll have basically this kind of shape, which is linearly increasing. So starting, like if the value of AV is 0.5, if the value of AU is much smaller, the degree of dominance will be 0. It starts to grow until it becomes equal to 0.5. And from 0.5 on, then we will say that U fully dominates V. That we incorporate by using a formula like this one. And again, to have the full fuzzy dominance relation using all the attributes, we can take the minimum. So looking at the matrix, in this case, it's still reflexive. An object is considered to dominate itself to degree 1, but it's no longer symmetric, right? So the degree of dominance of 1 over 2 is different than that of 2 over 1. And there are also, like before, some transitivity property is inside of the relation. Good, so that is one reason why we might want to consider fuzzy rough sets, fuzzy relations inside of rough set theory. A second case would happen when we look at regression problems. So again, I'm taking a simple data set. Now I'm trying to predict the price of an apartment. And we have again 3 attributes, like how close is your apartment to transport options, how big it is, and what is the distance to the nearest grocery store. And for the decision, in a regression problem, the decision would be the price. Now, we can, for example, try to approximate the concept expensive apartment. So for each price of an apartment, we would say it is expensive to degree 0.77, to degree 0.24, and so on. So basically, we make a monotone transformation from price to membership degree, which will be the decision of our data sets. So in this case, what we try to approximate, the concept will no longer be a classical set, getting bank loan, not getting it, but will be a fuzzy set. So mapping objects to membership degrees. And then the question arises, of course, now we have relations which are fuzzy, and we can have sets which are fuzzy. How to deal with lower and upper approximation in this case? And that is what I will explain in the following slides. So here, I'm going to perform a little bit of fuzzy magic, so to speak. So I'm going to show some formulas where first we will rephrase the conditions to belong to the lower and upper approximation in the traditional case. So lower approximation meant the equivalence class of U should be Fullian in A. We can restate that using quantifiers and logical connectives, saying that for all objects, if 2 objects are the same, VU belongs to E, then V should also belong to A. And similarly for the upper approximation, there should exist some object that is indiscernible from U, and V belongs to the concept. So that magic that I was talking about now happens. So we will replace A by a fuzzy set. We will replace equivalence relation E by a fuzzy relation, either dominance or indiscernibility. And in this case, so the results, lower and upper approximation, will also be fuzzy sets. So there will be the degree of U belonging to the lower approximation of A under R. And how do we get that? Well, we just translate, we extend those quantifiers and logical connectives. The for all, for example, the for all quantifier will translate to taking a minimum. The exists will lead to a maximum. On the other hand, for the implication connective and for the conjunction, we will have so-called fuzzy implications and triangular norms or T-norms. So basically those, I'm not giving the definition here, but those are operators which take 2 values between 0 and 1 and give you an implication value or a conjunction value also between 0 and 1. So they extend classical implication and conjunction. So in that way, we get the definitions of fuzzy lower and fuzzy upper approximation. Nice. So we can apply that to our data because we already, we will do that in this case only for the bank loan data. So in this case, if we take the indiscernibility matrix, so the one that I computed here, that will be our fuzzy relation, and the concept will still be the sets containing object 1, 2, and 4. So the decision will still be a classical set. Then we can, using the formulas from the previous slide, compute the membership degree of the objects to the lower and upper approximation. And we can see, for example, for the lower approximation, objects 1 and 2 do not belong fully to it. They have some membership degree, which basically is saying that there is some partial inconsistency between them, which causes them not to, or some partial inconsistency with other objects, which causes them to be not fully belonging to the lower approximation. In the same way for the upper approximation, so we have the first 4 objects fully inside there, just like in the classical case, but 5 and 6 also are added to some extent to the upper approximation, taking into account the partial or fuzzy inconsistencies. Okay, so we can do the same for the dominance. I will not show that because the idea is the same. But now looking at the scope of applications that we have for fuzzy rough sets, basically everything that we used rough sets for, we can also do it with fuzzy rough sets. So the whole supervised and unsupervised learning framework, we can extend it. We can look for fuzzy reduct, so we can try to reduce our data, taking only the object, only the attributes which preserve the consistency. And in this sense, I think some more than 10 years ago with Dominic, we had a paper how to obtain that. Also, we have a lot of instance selection approaches where we will try. The idea of those is that we will eliminate objects not fully or not enough belonging to lower approximation to make the data more consistent as a pre-processing technique for other classifiers. Classification is an important one, and one which I'm going to exemplify by an application called fuzzy rough nearest neighbors. So it's an approach which is a lazy learning approach, and it's very simple. So the idea of fuzzy rough nearest neighbors, so you have, in this case, again, a binary classification problem. You need to distinguish the circles from the squares, and you need to say for the test instance y, is it a circle or a square? So what you will do in this case is you will compute a lower and upper approximation of all the concepts, and then evaluate for the test object to what extent it belongs to those lower and upper approximations. And you will choose, or you will predict the concept which has the highest average membership degree in those two approximations. So that's a very simple instance-based approach for putting fuzzy rough sets to practice. And actually, we used it in a lot of applications using specific kinds of data, like, for instance, imbalanced classification, where one class is overrepresented and the other ones are less represented. And also in other data frameworks, where, for example, in the multi-label context or a multi-instance context. But, so one thing, yeah, this is a lazy learning approach. Of course, the question is, can we also do rule induction based on fuzzy rough sets? And for that, we need to investigate the granularity of fuzzy approximation. So the question will be, can a fuzzy lower approximation, like you can see here in the slide, so the green trapezoid, the lower approximation of the blue fuzzy set, can we still represent that as a union of simple fuzzy sets? Same like in the beginning with Pavlak rough sets, we represented lower approximation as a union of blocks of a partition. Yeah? And that question, well, it can be answered in the affirmative. So we can do that. And this is actually due to some of our Chinese colleagues who 10 years ago introduced the concept of fuzzy granules. So they are defined here on the slide, and also what it means to be granularly representable. But maybe it will be clearest if you look at the figure on top. So basically, for every object which to some extent belongs to the lower approximation, so we will have some triangle, like the ones that I've shown before using the fuzzy indiscernibility relation. And those triangles, so their height, will be determined by the degree of membership. For instance, the attribute value 0.5 belongs to its to degree 1, so it will have a bigger triangle than the other objects with less membership there. So in this sense, we can indeed say every granularly representable fuzzy set with which is defined as in the second equation, corresponds to, the fuzzy lower approximation is a granularly representable set. And again, we will make that shorter. We will say a consistent fuzzy set because of the last formula there, which says that, well, A can be represented as such a union if it is consistent. And what do we mean by consistent? Well, the inequality there, what it says, so T is a conjunction, and the conjunction of the degree to which V is related to U and the membership of U to A should be not bigger than the degree of membership of V to A. Basically, that means that if V and U are related and U belongs to A, then V should also belong to A. And that's basically what we call the consistency criterion in the classical case. So still in the fuzzy case, we have the same idea of consistent fuzzy sets. Lower and upper approximation will be consistent fuzzy sets. And actually we have the same result, that the lower approximation, as we define it, is still the greatest, the largest consistent fuzzy subset of A, while the upper approximation will be the smallest one that fully encloses the fuzzy set A. So we have that same result. And also interesting to mention, remember I talked about the Kotlowski-Slovinsky monotone approximation. So the closest consistent fuzzy sets, consistent sets to a given set, well, that can also be generalized. And this is the work of one of my students, Marko Palangetic, who actually will defend his PhD this month. So he already finished, and his work is currently under review. But what we did together with him is to do the same, like to try to find the consistent fuzzy set, so the union of fuzzy granules, which is the closest as possible to the original concept. Yeah? So it doesn't have to be a lower or an upper approximation. It should be as close as possible, again, with respect to some loss function. And that can also be used instead of those lower and upper approximation. So once we have those granules, those are the building blocks that would be used for rule induction. Now, to induce a rule is not a lot of problem. A fuzzy rule, for example, if we look at the first instance, we can make a rule like if the det is around 2200, with around defined by the similarity relation from a few slides back, right? And if the salary is around 4,200 and the portfolio around 6,000, then we can say that the decision is 1. Okay? So we can have rules based on lower, upper approximation, or based on the granular approximation of Marko Palangetic. And with a certain degree, then we can obtain that the decision will be 1, will be to get the bank loan. In a similar way, we can replace indiscernibility, similarity, by dominance. So the second rule would be a dominance-based rule where the det would be approximately lower than 2,200, and the same for the remaining attributes. So constructing rules is not a problem. The main problem and the main challenge at this point is how to extend algorithms like the LEM2 algorithm or the ModLEM algorithm to fuzzy rough sets, because they have some particular intricacies like stop conditions, how to know if a concept is fully covered by some granules. So that requires still some work, which we are in the progress of starting up with a new PhD student, to design both efficient and understandable extensions of those rule induction methods. So that is one of our current main challenges. So that about rule induction. The second topic I want to talk about will be robust fuzzy rough sets. And what do I mean by robustness? Well, if we take a look again at Pavlov's original representation, we can see that outliers, which means objects which like do not satisfy the standard distribution of the data, that they can confuse the lower and upper approximations. For instance, assume that there is one object which is far away from all the other examples from A, but included into A. So that would mean that the upper approximation would suddenly become much larger because it also has to include that faraway object and all of its indiscernible objects. In the same way, if we have some objects inside, so very close to other examples of A, but it does not belong to A, that can suddenly change the lower approximation to become a lot smaller. So one change, an object in one change can lead to a big change in the rough lower and upper approximations. Now, this is a property which is not solved by standard fuzzy rough sets, because if we look at definitions at the bottom of the slide, they include a minimum and a maximum. So that minimum was used to extend for all quantifier, the maximum, the exists quantifier. So it's still possible if one object, for example, is fully similar to another object V, and one of them belongs to A and the other does not, well, that will make both objects to fully not belong to the lower approximation. So the minimum is a very strong operator. In the same way, the maximum, of course, is a very generous operator, which will add a lot of objects in a large degree to the upper approximation. So that can be a problem, like for instance, if we want to generate rules based on those approximations to get information which is too vague, too general. Okay. Now, of course, rough set theory has thought about that also outside of the fuzzy rough set framework. So already in the beginning of the 1990s, Professor Ziarko introduced the variable precision rough set framework. So the idea there was that instead of asking that all elements of the equivalence class belong to A, we will be satisfied if at least some high fraction belongs to A. For instance, if 95% of all the objects similar to U are in A, well, then U can be considered to be part of the lower approximation. In the same way, we can make the upper approximation also more flexible by saying that more than some given fraction should belong to A. Not just one object is enough, but maybe like 20 or 10% of the objects should belong to A in order for the whole block to be included in the upper approximation. So the idea is to weaken those quantifiers. Now we can take that one step further and take that to the ambit of fuzzy logic by replacing those standard crisp quantifiers by fuzzy ones, by not saying at least some fraction or at more than some fraction, but saying most of the elements should belong to the concept for an object to belong to the lower approximation. And the same for the upper approximation. So we could have some elements, where some is some vaguely defined concept, can be used as a condition to define the upper approximation. And this leads to the framework of vaguely quantified rough sets, VQRS. We chose that term because it sounds very much like VPRS, variable precision rough sets. Now, a bit more about how can we model those fuzzy quantifiers? How do they look? Well, first of all, a fuzzy quantifier that will be, again, some mapping from 0, 1 to 0, 1. Basically, we are saying for some fraction, to what extent it's considered some quantifier. Yeah? For example, let's take a look at the exists quantifier here on the slide. So that would be 0 if the fraction x is 0, but as soon as the fraction becomes larger than 0, it's already 1. And the for all quantifier, it's a bit opposite. It's always 0 unless the fraction is exactly equal to 1. Okay? And we have similar quantifiers for the at least P or more than Q, which are used by VPRS. Okay? So all of those are examples of so-called regularly increasing monotone quantifiers. Then a mouthful to say each time, so we abbreviate it as RIM quantifiers. RIM quantifiers will be 0 in 0, 1 in 1, and they will do some monotonously increasing function in between. So the ones at the bottom, they are just two-valued, either 0 or 1. But if we want to have examples of real fuzzy ones, like for the ones that we will use for sum and most, we can use a formula like this one. So based on some parameters alpha and beta. For example, in the left figure, you can see that up until, so from the beginning, from 0 up until 0.6, there will be some increasing function. From 0.6 onwards, if a fraction is at least 60%, it will be considered sum to degree 1. And for most, we have a more strict function, meaning it will be 0 until 0.2, and then again start gradually to grow higher, and only when it's 1, it will become also 1 as the degree. So here we have those such shapes for fuzzy quantifiers. Now, how to use that in the vaguely quantified offset model? Well, what we will do is we will evaluate the fraction of an equivalence class included into the concept A by means of those quantifiers. So what you have between brackets, UE intersection A divided by UE, that means the fraction of the equivalence class, we're talking now about Pavlak offsets, into A, that fraction. To what extent is it considered, for example, Q1 most or Q2 sum? Okay. Or we can have, clearly, if we use for all for Q1 and exist for Q2, we just get Pavlak's offsets again. Okay. Because basically we're saying that the fraction of UE included into A, that fraction should be 1. And then it belongs to the lower approximation. The same way, we can obtain variable precision offsets, VPRS, as a special case using the at least P and more than Q fuzzy quantifiers. Now, the VQRS model is theoretically, like intuitively, it's very nice, okay, because basically it just goes along this line of that was presented here. All becomes at least a fraction, becomes most. Okay? Intuitively, that's very nice. But in practice, it has some drawbacks. And those drawbacks are not only due to the use of fuzzy sets, VPRS also had them. And one of those drawbacks is, for instance, the property of relation monotonicity. Relation monotonicity, what does that mean? Well, I show it to you here with an example for Pavlak offsets. So suppose in the left-hand figure, you would have a VPRS lower approximation of the concept A. So you can see it contains some blocks not fully in A, but they are added to the lower approximation because a high enough fraction of them is inside A. Now, what happens if we make the partition finer? So for instance, we add another attribute, so objects which before were in the same equivalence class now can be distinguished from each other. They will be in different blocks. Okay? Normally, we would then expect the lower approximation not to become smaller. But unfortunately, it's quite possible with VPRS that it happens, because you can see the blocks on the left-hand side, they are divided in 4 new blocks, and 2 of them are no longer inside of the lower approximation because their fraction of includedness is too low. So you can see some intuitive property which classical offset had, VPRS, and therefore all of its extensions, will no longer satisfy. And actually, it may not seem like such a big deal. In some cases, it is not. But there are applications, like for instance, incremental approaches where reducts are sought. I think also for rule induction it applies, that you cannot or you need that property. So VPRS and VQRS can de facto not be used there. So that's, at that point, inspired us to leave aside the VQRS model and focus on another one. So what we did, we went back to the formula for the lower approximation with the minimum, and we decided to replace that minimum by something else, something more general. And this is the OWA, or ordered weighted average operator. So instead of taking just the smallest of those implication values, we will take some aggregation of all those values. So we will look at implication values for all V in U, and we will order them from the largest to the smallest, and then we will weight all of them. In the classical minimum case, we would just weight the last one. So we would have a vector of zeros and then one at the end. Yeah? But with OWA, what we will do is we will can have also some weights for the other positions. So we will take some increasing weights to reflect that the higher the implication values, the lower the associated weights should be. And we want to give weight not just to the last one, but also to like the second last, the third last, and so on. So that's the idea of the OWA-based rough set model. We can do the same, not just for the lower, but also for the upper approximation. And there the weights will be applied to the T-norm, so the fuzzy conjunction of similarity or relation and membership. And we will use decreasing weights to reflect the idea that we will not just weight the first one, the highest, but also the second highest, third highest, and so on. Okay? So that's our idea there. We have a lot of good news about OWA-based rough sets, which is also why we have been using them for a lot of our applications. First of all, that problem that we mentioned about relation monotonicity, OWA-based rough sets don't have it. So if you make your partition or your relation finer, your lower approximation will grow. So exactly as you'd expect it to be. Also some more recent results, which we didn't know. So Marko, the student I told you about, Marko Palangetic, he was able to prove that those OWA-based approximations, so the ones from the previous slide, they actually are also consistent fuzzy sets. So remember, a consistent fuzzy set was one that we could write as the union of simple granules, fuzzy granules. Well, Marko showed that if you take the OWA operator with some conditions, then the lower and upper approximation can also be written like unions of those fuzzy granules. And that means basically that a rule induction algorithm can also be applied to them. So we can include the robustness and still get rule induction algorithms to work. That is one result. Another result is by my other student, Adnan Terens, who is present today and who will present a talk tomorrow, is about the link between OWA-based rough sets and the VQRS model. Because, like I said, we abandoned the model with fuzzy quantifiers, yeah? And we changed it to something based on OWA operators, which kind of is unintuitive because OWA, it's a vector of weights, how to interpret that. But as Adnan showed, to every of those OWA weights, we can actually construct a corresponding rim quantifier, so a fuzzy quantifier which satisfies the idea of the VQRS model. So that means is that OWA-based approximations can also be read as VQRS approximations. So for instance, an instance belongs to the lower approximation if most of the instances in U belong to A. But there is one small detail, and that's shown here. So in VQRS, we had if most instances in U also are in A, but here we will have for most instances in U, if they are related to U, then they should also belong to A. So that means also objects which are not related to you are taken with us into the equation. So that means a more general quantification that somehow shifts a little bit the idea of the lower and upper approximation. So those are good things about OR-based rough sets. There are also some negative things. I already mentioned that it's kind of difficult to interpret weight vectors. Quantifiers is easier. We could mend that somehow by this transformation to rim quantifiers. Another thing is that OR-based rough sets, they will weight instances like just based on their position. We just calculate all those implication and P norm degrees, and we just order them, and then we apply some fixed weight vector to them. Of course, like every data set requires a different OR vector. So not one which will work well for our bank loan data, which would not work well for the next problem. So how to solve that? Yeah, one way is, of course, tuning the data, tuning the vectors according to the data. So changing the weights, but that's inefficient. Like the search space is quite large. The possible weight vectors that we need to consider is large, and also how to interpret those changed weight vectors for each different data sets. So that's why we started thinking about other ways, like not just treating objects symmetrically, but like approaches where particular subsets of the data are singled out. For instance, suppose that we know that some part of our data, those are outliers. Or suppose that we know some part of our data was measured according to some inferior mechanism, and so we don't trust those data so much. With OR-based rough sets, we can't model that. Yeah, we can just look at those implication and T-norm degrees and do some transformation of them. But with the Choquet model, so the Choquet model is based on a Choquet integral, another aggregation operator, we can weight specific subsets. So we can say those outliers, we can give them specific weights, and we can say that an object belongs to the lower approximation if all the similar objects, except maybe those outliers, are also in A. Yeah? So that's kind of a novel direction. Recent results were published in a paper in International Journal of Approximate Reasoning, and additional results about the link with fuzzy quantifiers will be given tomorrow if you attend the session in RSTA at 10 o'clock by Adnan, who will talk about our joint results. So the final topic, which I will only touch briefly on, is, well, it's because it's a very hot topic, and it's also a topic that we are very interested in. It's explainable or interpretable machine learning. Okay? The idea is, okay, our classifiers generate predictions, but we want to be able to explain to a novice user, to someone who is not familiar with the workings of the classifier, why it predicted that, that result. And first, I will talk about the lazy learning approaches. So for instance, the fuzzy rough nearest neighbor algorithm, which just looked at the lower and upper approximation of the test instance for the different classes. So for that, the positive thing is that it's quite easy to identify which are the responsible object, because it's the ones which are the closest, the nearest neighbors, which will have the highest lower and upper approximation, or will cause the highest lower and approximation degrees, and they so can be returned to a user. And as an example of a topic or a task where that is actually useful, I refer to another student of mine, Olga Kaminska, who is doing a PhD on emotion detection from text. So basically what she's doing, she has a big text collection. Usually it's tweets, and these tweets are modeled according to some like word embeddings, like there is word2vec or BERT, maybe you're familiar with them. So what they do is they replace the text by numerical vectors of a high dimensionality, hundreds or maybe thousands of values. And the idea is we want to detect if some text, some tweet contains some emotion, if it is an example of a hate speech, if it contains irony, and such related topics. So at the bottom of the slide, you can see an example of an explanation for our anger detection task. So the idea is to predict to what extent a tweet contains a level of anger. So the test tweets would have would look like, I know you mean well, but I'm offended, prick. And the prediction would be that it's considered to be angry to degree 2, where the degrees are between 0 and 3, so quite angry. So if we want to look at the explanation or why that kind of prediction was made, so we look at the neighbors of the tweet. So the neighbors will be the closest tweets according to that vector embedding approach, and all of them would consider the word offended. Yeah? So in this case, presenting those similar tweets can give to the user quite a easy idea as to why that prediction of quite angry was made. So that's for the lazy learning approach. Now, lazy learning is one thing, but it doesn't always work well. Like, for instance, in the case of the tweets, we have hundreds of attributes, so it's still kind of acceptable rather to say something about similar tweets than to say like attribute number 355 and 476 were responsible for the prediction. In other kinds of problems with less attributes, less relevant attributes, or more understandable attributes, fuzzy rules, we believe, would give a better or more understandable approach. For instance, first of all, same like in the lazy learning approach, it's easy to pinpoint what is the knowledge which is responsible for the prediction, because now it will be one or more fuzzy rules which are fired and which generates that prediction. Also, inside of those fuzzy rules, if they are compact, we can try to check which of the attributes are the ones which are the most relevant for making those predictions. So we believe here there's a challenge for fuzzy rule induction to take that also to explainable, to a level of explainability. And actually, there's a whole branch inside of fuzzy logic, researchers who are dealing with exactly that, with the interpretability of fuzzy rule-based systems. And then a final thing, related somewhat also to fuzzy rules. They're not exactly decision rules, but they are more like summarization rules. For instance, you have a data set, and then based on those data, you want to make some global appreciations of relations in your data. Yeah? Like in a data mining approach, where you have association rules, for example. And then the fuzzy quantifiers, the fuzzy, more generally also the fuzzy labels, like low and high, they can be used quite well for generating flexible and understandable knowledge. Like, for instance, from the data set, we could infer that most of the applicants which have low debt and a high salary are likely to get the bank loan. So that is also some area where we think that use of fuzzy logic can be beneficial. So to end my presentation, and with the picture, I hope that I was able to convince you that fuzzy sets and rough sets, that they both have useful characteristics and that they can be combined usefully to get an end product which combines both inconsistency and gradual characteristics. So, and they have a lot of applications, both in the machine learning practical side as in the theoretical side, regarding, for example, ideas about granularity of the different approaches. That's all. Thank you very much.
Thank you very much one more time. I think we have the time for one or two questions from the audience. Do you have any questions?
Okay, thank you, Professor Chris. Thank you for your brilliant talk. So can you referring to your page 10?
Huh?
Yeah.
Can we get the presentation back?
In your slide 10, you mentioned a simple case about the loan salary and the debate and the
Lower and upper.
I think can you maybe one more you go to the table you have some
The table.
the correlation matrix, yeah.
The matrix.
Yeah, the correlation matrix. Because my question is actually, because from here, right, I look at this one. For example, you say your decision is the 1, 2, and the 4, right?
No. In the matrix, so
Yeah.
the rows and the columns are the instances. So 1 is related to 1 to degree 1.
Okay.
Yeah.
Yeah, because now my question is you look at your right side, that one.
Yeah.
Because my interest is on the 1, 2, because they both belong to the decision 3. Decision 1.
Yes.
And the 3, 4, actually, they are the duplicated records, but
Yes.
because due to the different decision 0, 1.
Yes.
So my question is, because here I only show the 3 features, right? Then how do you know which one is the outlier or which one is the black noise or white noise? Because if I look at the value, right? If you see the 1, for example, your instance 1, then actually to the 3 and 4, the score is the same.
Yeah.
0.552 and 0.52.
Yeah.
And you to the 4 also roughly the same.
Exactly.
So, and the 2, your instance 2 to the 3 and 4 also is the same, 4, 1, 2. And so now my question is actually, how do you identify the 3 or 4? The instance 3, 4 is a noise, yeah, something here, yeah.
We don't
because
know.
you only have 3 features, yeah.
Exactly, that's the main problem. We probably don't have enough features to characterize the whole data and to be able to generalize to new patterns, because obviously something else was responsible for the decision of the bank manager to give a loan to 4 and not to 3. And that information is not present. So rough sets cannot solve the problem, because it's not an idea of generating more knowledge. It just like shows you, here's the problem. 3 and 4 is the problem. Or if you use fuzzy rough sets, like 1 and 3 is a problem to some extent. So like rough sets and fuzzy rough sets are the doctor which make the diagnosis, but they will not solve the problem of adding more data. That's something that only like someone who collects the data might want to look into that and see what additional attributes are responsible.
Okay, because from this paper, right, I can see for the decision 0, but I can see the difference actually. For example, your instance 3 that match to the 5, 6.
Yeah.
Yeah, I can see the difference actually to the 4 and 5. I can see the difference. That means he can get some clue from here. Yeah, so interesting. Yeah. Okay, it's okay. I know because the feature is only 3 features, we cannot really do anything. Another question is about your last slide. You are talking about the hot topic. Actually, this morning our chair also mentioned about the explainable the AI, right? Because you mentioned one of your student case actually about the Twitter, the anger. But actually my interest is from here I can see you based on the dictionary, like your word dictionary, everybody mentioning the offender. But actually in the real case, right, we never see offender. We will say, okay, it's too much praise or something. We always use negative words, but actually what I'm talking about. That means we're not really so straightforward to mention some word like offender. So in that case, your fuzzy, this model, can you really do something on this? Because I also did some the sentiment the Twitter analysis before, so I roughly want to listen to your advice about the fuzzy. For example, I'm quite interested in your OWT, right? Your OW model. I think that's quite nice model. Yeah. Okay.
Yeah.
Thank you.
Okay, but yeah, in this case, it's clear that the words offended is the one which is recurring. It will not always be like that. That there's a single word or a single phrase which obviously is responsible for the prediction. But the idea of the lazy learning rather than a neural network would just say, okay, I predict anger level 2, and these are the weights of my neurons, for example. Here, at least, you're able to say, I predict number 2 because these 3 or 4 or whatever are the nearest neighbors in my data. They look like your tweets, and they have the same or similar anger level. So that's the idea. We want to take that black box, we want to replace it by some concrete examples. So for the text example, it makes sense because like giving attributes to show that like we are similar in this attributes, if there is like a 600 numerical vector, 600 position numerical vector, that will not be useful. So just giving some simple linguistic text fragments as a motivation, I think that that's actually quite helpful.
Thank you very much. Thank you very much for very interesting discussion. And Chris, thanks a lot one more time for great talk. And you are with us today, tomorrow, so we can discuss more.
Thank you very much.